Hi, my name is Denzil Ribeiro. I am a principal program manager at Microsoft and work primarily on the Azure SQL Database platform and specifically on Hyperscale. So, welcome to this session. Thank you for taking the time to learn about Hyperscale. So, we'll look at the benefits and use cases of Hyperscale. We'll look at the architecture and some troubleshooting and diagnostics. And last but not the least, practices in terms of performance as well as migration. So, Azure SQL Hyperscale is our cloud native solution that addresses many of your traditional VLDB management challenges such as how long will it take to back up a 20 terabyte database, and how can I restore that in a reasonable fashion, as well as provide HA and DR and all those other needs that VLDBs do have. um, it is also an attractive platform for databases of any size because of a great to performance ratio that we'll talk about in a bit. Uh, some of the benefits are categorized in various areas. So, from an availability and performance perspective, the separation of compute and storage on hyperscale enables rapid scale up and scale down, which is regardless of any of the data size. So, it's constant time from that perspective. And it's in the seconds range to be able to scale up or scale down. Um, Compute or within a minute. Ingestion is also, we enable a high rate of data ingestion. Rate of data ingestion is fixed irrespective of compute size. In other tiers, the rate of ingestion or log generation rate is a ratio between compute size or it's correlated with compute size, whereas it's not in hyperscale. We also enable point-in-time restore or database copy within region, which is fast regardless of data size because these restores are done based out of snapshots. Um, some of the traditional activities that happen on compute, such as backups and checkpoints, are now offloaded to these page servers, thereby saving precious resources on compute. We enable horizontal scale out with addition of 4 read replicas to scale out your read workloads. And then from an HA perspective, failover time is on par with business critical. So we are talking in the seconds to failover in case of an outage or patching or upgrade. The performance, by and large, is better than standard or general purpose because of multiple layers of caching, which we'll cover in the architecture. And we have SLAs that range from 99.9 to 99.99%. There are still some workloads that require extremely low latency log commits in the 1 millisecond range, which are better suited to business critical than hyperscale at this juncture. And you are working to close that gap. From a size perspective, we support up to 100 terabytes, and data and log storage management is pretty much automated. So, data and log will grow as the need grows. The most common use cases are OLTP, which is very well known. It's for databases of any size for OLTP. Other common use cases are real-time analytics or HTAP, as well as the SMP type of operational data stores or data warehouses. And last but not the least, the new breed of modern applications with things like IoT. So we are not going to cover the OLTP scenarios because relational database has been great for that for ages. Some of the new scenarios of patterns we are seeing with hyperscale, one of them is near real time, fraud detection or analytics of any sorts, where data originates on-prem or on the cloud. So if it's on-prem, it's then shipped to Event Hub, or Event Hub is the source of all the incoming data. It lands into Event Hub or IoT Hub, depending on if it's an IoT scenario or not. This data then could be picked by Azure functions. Arriving data triggers an Azure function, which then pushes that data up to Hyperscale in micro batches using bulk copy. And then the scale out scenario on the read side, that data is then shipped to multiple replicas, which then can serve 80 cores per replica. You can scale out effectively 4 replicas, read replicas times 80 core plus 1 read write primary. The other scenario is data marts, of course. We have great columnar or column store support, which makes data marts extremely performant. And Hyperscale is no different. Enabling a larger size than other tiers has enabled some scenarios on Hyperscale which weren't possible on the PaaS services before. So these are more of your ETL workloads, which data is ingested via either ADF or Azure Data Factory or Spark or any other ETL tool, and then lands in. You can have there are scenarios of a hub and spoke type model where all the data lands in the Azure Data Warehouse, as well as client specific data or subsets of data land into different marts. And then applications connect to the SQL marts, whether they are SaaS providers exposing a mart per client or SaaS apps interacting with these, such as dashboards and such. So load on primary, some of the patterns are load on primary, query across replicas, or load and swap if you have kind of the truncate and load scenarios. And databases are in the 5 to 20 terabyte range. Now let's look at the architecture of Hyperscale. How is Hyperscale actually put together natively in the cloud? So there are three main components in Hyperscale. You have the compute. Compute is totally stateless, and that's where the user interacts with. So this is just a stateless compute hosting SQL Server.exe and has a local SSD cache. And the components below are system provision. So it's not like a user provisions it. We automatically provision these components. And that's page servers. Page servers are covering cache for all your data. And then that data is backed by Azure Blob Storage. And then you have the log service. So all the write activity happens from compute to log, and this log is then shipped to other components. But these are system provision components, and user only interacts with compute. From an architecture perspective, we have a separation of compute and storage. All writes, and you'll see below, the log pathway is in red, the data pathway is in green. All writes end up in the log service, which is externalized. So this is not on the compute itself. The compute has a local cache, and then this log service then ships this log to all these page servers. And these page servers cover a chunk of the file, or a file each at this point, which is 128 gigs in size, and they have replicas. And log is shipped by this log service to this covering cache, if you will. And then each of these files are backed up by Azure standard storage. So these files exist on Blob. The log service also destages these logs for longer retention. So the log service has a finite storage space here, if you will, and the longer term storage is on Azure Blob Storage. And last but not the least is when a user actually reads a page, that's the data pathway. If the page does not exist in the compute's buffer pool, it reads from the page servers. And the log service responsibility also is to ship log to the replicas. So the primary here in this case does not talk to any of the secondary log replicas. Um, the primary only talks to the log service. The log service ships this log to the log replicas. There is redundancy at all tiers. So you have replicas for page servers. That's backed multiple layers of caching, so on and so forth. There's a 100 terabyte supported limit. As you can see, the compute being stateless, the separation of compute and storage. And then all the communications are done through this RBIO protocol, which intercepts the IO and actually ships it to these various components. Next, let's talk about the log service. The log service is an externalized log service. It's a single writer and multiple consumer or readers model. So it provides an infinite log abstraction. So there isn't a limit per se for the log, and consists of three components primarily. One is the xlog process, and we'll go through this in a bit. The second is a landing zone, which is your durable commit point. The third is a long-term storage, which is your overflow destage area for long-term retention of the log. So the landing zone currently is Azure Premium Storage. It's a 1 terabyte disk, and it's your durable commit point. What that means is for a transaction to be committed on compute, it has to be written to this landing zone. And we're talking about 2 to 4 millisecond commit latency. It's structured. It's structured into VLFs, just like they are on kind of normal SQL Server, except they're fixed size VLFs. And the VLFs have log blocks which are flashed. And then the xlog process actually has a log broker, which is an in-memory area. The broker effectively services request for logs from page servers and replicas and such. So it's a pull model. So each of these components requests for a log block from the broker, and then there's a tiered read. If the log exists in the broker because the broker is in memory, it's pulled from the broker. If not, from the log cache. If not, from the landing zone, and if not, from Azure Standard Storage. So it depends on which area of the log is being requested, whether it's pulled from these. But most of the requests should be serviced by the broker. The xlog process is also responsible for destaging log to long-term storage. So effectively, for the retention period, effectively, which is 7 days. Next comes the page server. The page server is a fully covering cache. They equate currently, it equates 1:1 to files in sys.database files. So if you look at sys.database files, the number of files, each file has a corresponding page server or page server pair. So it's 128 gig files, and every new database gets 128 gig files. And this RBPX cache is fully covering, which means all those 128 gigs are in local SSD of these page servers. And each page server has a replica. So the page server, there is no write from compute to page server. And information or pages updated or log records are applied, by replaying log to update its pages. We talked about the fact that it's covering already. So a read from the page server is more expensive than a read from the non-covering RBPX cache on compute because it's a remote read. But otherwise, the page server has local SSD. Each page server on its own has its data file on Azure Standard Storage. The page server offloads some of these computations such as checkpoints. Checkpoints are executed on page servers, not on compute, because the compute does not write to page servers directly. Similarly, backups are done with file snapshots of the files on Azure Standard Storage. The page server is a service fabric application with a replication factor of 2. What that means is each page server has a replica. So when we do things like patching, we'll spawn another replica and apply the bits and then fail over. So so effectively there's HA or resiliency built in. I didn't mean we spawn a new replica. If one of these replicas or nodes goes down, we will spawn a new replica to take its place. So there's always a primary and a secondary replica of the page server. Both replicas though are independent, so they don't talk to each other. Each of them has their own files. Each of them service their own requests. The compute itself, when you're asking for a page, maintains a quality of service to both the replicas. And so if one replica quality of service is much better than the other because that's being rebooted, patched, upgraded, whatever, then pages are requested from the replica which is ARPO has the better quality of service. But they otherwise serve, both of them serve active requests from compute, right? And that also there's also storage redundancy from a file perspective, as well as one of these accounts is a GRS account, which is a geo-replicated storage account, so that snapshots are available on the paired region to restore from. The readable secondary is just like a compute. Currently, it's the same size as the primary, so there's no difference in terms of number of cores. It is a hot failover target, so if you have a compute replica, if you have no secondary, and your primary compute crashes or goes down, or the node goes down, we will have to spawn a new compute replica and attach it or to the page servers of the hyperscale distributed system. If you have a readable secondary which is up and applying log, failover, it's considered a hot failover target. Now the thing to remember is there's no direct communication between primary and secondary. So unlike business critical, which is based on always on availability groups, in Hyperscale, the primary replica does not talk directly to the secondary replica. All the communication is done via the log service. And so replicas apply this log asynchronously. So what that means is there can be a milliseconds delay between what the primary sees and the secondary sees. And log is applied only to the pages which are in buffer pool or RBPX. If a page is not being in the buffer pool or RBPX because the query hasn't requested it, log isn't applied. If that page is needed on the read, this replica will talk to the same set of page servers and get that page from the page servers. Once it's in buffer pool and RBPX, log is applied to maintain it. So what's the use of readable secondaries? Of course, it is to scale your read workloads, number one. You also have a higher SLA with replicas greater than 0, and they are priced at Azure Hybrid or AHUB pricing, which is less than the price of primary compute with license included. So let's tie this all up, from a write IO perspective. Let's see how this flows. You have a write transaction, an application which is actually committing a transaction on the primary. The first thing this has to do is this transaction has to actually land on the landing zone before the commit is returned to the user. At the same time, this transaction or log block is sent to this pending area of the xlog process, which is then populated into broker. Right? So broker is what this xlog process then, the broker distributes that log or serves the get log requests from different actors like page servers in the system. But the durable commit point is landing zone. When a secondary request from log from the xlog process, broker services that log. Right? So the log then ages out from the landing zone into local SSD cache um, uh, called the log cache here, and then is destaged finally to Azure Standard Storage. Right, so that's kept for the retention period. On a read, on the other hand, um, if for a new database or if all the other components, the durable storage is Azure Standard Storage. So you have your files and your data files and your backups, which are snapshots on Azure Standard Storage. A page server, when a page server is brought up for the first time, it reads that file from Azure Standard Storage. So seeding occurs if it's a new replica of the page server, because the prior replica, went down or was whatever, the node had hardware problems or something. If a page server comes up, it's seeded from this blob. But once the page server is seeded, we never actually read from the blobs. It's only for the initial seeding. Everything is then covering in the local SSD cache of the page servers. Page servers will then populate a non-covering cache depending on reads. So if a read is done of a page which is remote, so a user reads a page, right? If the page is in buffer pool, the page is returned. If the page is not in buffer pool, then it goes to RBPX. If it finds it in RBPX, that read request never leaves the primary or secondary compute, right? If it does not find it in RBPX, then the primary issues a get page for that page and says, give me this page, say a page 25 at a particular LSN. If the page server has that page at that LSN, it returns immediately. If that page is not caught up to this LSN, then the page server requests for log from the log service, applies that log to the page, and then returns the page. So effectively, I mean, if the data is in buffer pool, your response time is almost immediate because it's memory. If it's in local RBPX, we're talking 1 to 2 seconds. If it's a remote page read from page server, then it is 2 seconds plus. And the plus is in particular if a page server is behind in applying log and has to apply the log, then that time accounts for the get page call. Then the page is returned and all is good. So next, let's look at a demo which we look at horizontal scaling on Hyperscale. So here we have a Hyperscale database, and if we look at this, this is a 80 vCore database. It's around 4 terabytes in size, and we're going to run a workload on it as we speak now. So let's go to my workload driver, if you will. So a couple things here that you will notice. We have two parameter sets. One is my read workload and one is my write workload. One is executing with 150 threads, one is executing with 60 threads. And initially, we are going to redirect all of this workload to the primary, right? So we have a single replica, or effectively, we are not using read scale at this time. So I'm going to launch this workload, and I'm going to run it. And we'll come back to this in just a second. So while this is running, what I'm going to do is I'm going to go to configure. I know that I have a spike coming up in my workload. We can see that we have two replicas here. You have the primary and you have one secondary replica. So what I'm going to do is I'm going to bump that up to 2, hit apply, and come back to this in a second. While this is going, let's look at our workload which is initialized. You should see 2 windows of some sorts. Let's pull that out. So the write workload has around 300 transactions, between 250 and 300 transactions per second. The read workload has much more, and I think I messed up. the view. Sorry about that. So let me stop this and start it again. Sorry about that. Um, and I will just pull this out so that we see that in a second. So you're gonna see this plateau at around 200 odd transactions a second. The other one will plateau, closer to the 1500 or so transactions second. So as I said, so it's 1400, 1500 is where we are plateauing, and this is around 300 transactions a second that we are plateauing. So let's look at, I have a Grafana dashboard just to simplify things, um, where we actually are connecting to the same database. This is ATV core, hyperscale tier, and we'll see in a second that CPU is spiking, and we have around 4,000 or so batch requests a second. And soon effectively, I mean, this refreshes every 15 seconds. Soon CPU would be your primary bottleneck here, and latency would matter. So if we scroll further down to kind of the weights and queues analysis of things, you will see that our primary bottleneck in a second will be SOS scheduler yield, which indicates CPU is a bottleneck. Our secondary one is an IO latch wait. But even looking at the IO latch wait, a lot of that wait time is signal, or a significant amount of wait time, both in write log and IO latch wait, is signal wait time, which indicates that CPU is your actual bottleneck, right? And we see CPU is over 80% here in this case. Let's go and see what our stabilized numbers are. This is about 2000 transactions a second and around 270 or so, 280 transactions a second. Right? So I'm going to stop this workload right now, and I'm going to go back to the portal. The portal should have added already a replica. Yes, it said it was added 2 minutes ago. So adding a replica on the fly is as easy as waiting for the replica to be added in about 60 seconds or so. And effectively, so let's see what this workload can perform if we actually go to the read replicas. So I go to profile here. The only thing I do is I change this read scale out from true to false. So I'm going to make it true, or from false to true. And what I'm going to do is, since I have two replicas, I'm going to bump that threads up to 300 for only this read thread group. The ingestion thread group remains as is. And we go to drivers and we launch. And once we launch, we'll start that workload. It'll take a minute or two to stabilize, and we'll be able to kind of look at the numbers. While we're doing that, let's go and see executing requests. Now, if I look at the primary, only some select activity is going on because I have some selects required for the ingest as well, but I see ingest activity on the primary. This is connecting to the primary. And how do we know? I mean, today there's no easy way to connect to a specific replica. I'm looking at the host name here, which is db.48 for some of the local connections, right? So db48 is your primary. Similarly, in this connection string, connection options, I'm going to actually connect to the read replica. So I'm going to put the hscdb4tb connection, and then specify application intent equal read only. And I'm going to give my login and password and connect. And so I will see requests now. db.29 is my replica, and I'm seeing a ton of requests on my replica. And I see the CPU on my replica also is now going up. This is resource stats. So you see CPU on the replica is about 80%. And this is the output of the DMDB resource stats, DMB, which gives you your CPU, data IO, log percent, metrics for the single DB. Right, but you see the ton of selects, and yeah, they're doing some IO, some are waiting, some are not. But let's look at what that stabilizes to. And we can see here that there's pretty much linear scale. We are roughly over 2,000 transactions a second with one, just the primary. Offloading those read transactions to just two replicas, we are around 4,400, right? And more importantly, our ingest workload now has increased from what was 275 to 300 to more of the 420 mark, because there isn't a bottleneck on CPU which was contributing to some delays in the ingest workload. If I look at my dashboard again here, which is not the right dashboard, sorry. If I look at my dashboard again here and refresh this, you see the CPU was high when all the workload was being brought. Now CPU is barely at 15%, right? Or 5%. And however, the log generation rate has increased. Before it was closer to the 4 to 6 MB because there was CPU contention, and every write to the log actually, when it switched off the scheduler, required more time to get back on the scheduler. Now you can see the log throughput has gone up, though you're running the same number of threads and the same workload effectively. And latency of those writes has gone down. So that's the read scale in a nutshell. I don't have dashboards configured for the replicas per se, but we've seen the activity on the replica and the fact that CPU is now pegged on the replica instead of on the primary or on the set of replicas, and we have doubled our workload, as we've seen, from 2,100 transactions to more like 4,400 transactions. Best practices in troubleshooting. So from a performance perspective, the first thing to note is that, Hyperscale is just a tier. At the end of the day, all your SQL engine common, best practices still apply. It's still SQL Server. It's just a different architecture that enables us to scale and remove some of the traditional, bottlenecks and limitations. One difference from hyperscale perspective is, log generation rate is not coupled with compute size, so it's irrespective of compute size. Scale down latency, we've looked at a couple times. It's pretty quick. One thing to be careful is tempdb and rbpx, though are finite resources, are on local SSD, and the size is proportional to compute size, right? So while there is separation of storage and compute, your cache and your tempdb are a percentage of compute. And there is a vcode limit article which actually states that. Couple indexing kind of recommendations on the hyperscale side in particular. In index creation or rebuild, on hyperscale, sort in tempdb is enabled by default. So tempdb is used irrespective of if you have sort in tempdb in the create index statement, right? So if possible, use resumable indexes to create index on large tables. So you don't run out of the tempdb on a finite compute or a smaller compute. Number two is so that we can clear the log and all the other benefits that resume brings to the table. The other thing that can be something to consider is using a max stop hint for any index creation activities, because if not, you are going to consume potentially the log generation rate, and or in certain cases have contention on other primitives. So up to max stop 16 is probably fine. Max stop A is probably fine in most cases. Up to max stop 16 is recommended. Then from a tempdb gam scam contention, use memory optimized table variables. That's while in memory oltp durable tables are not available today in hyperscale, memory optimized table variables are. And then remember that secondary replicas are asynchronous. So if you have an application that banks on the fact that you've just inserted a row and that row has to exist on a replica, for those transactions that bank on that logic, they should go to primary because the secondary replica could be milliseconds behind. Um, and some operations are size of data. So if you do a geo restore, for example, it is a size of data operation. In particular, if you're doing to a third region, or cross-region database copy is a size of data operation, right? Anything that doesn't originate with snapshots is a size of data operation. The next thing from a performance perspective is resource management, right? So CPU, every database has a set of limits, and we document them in this single database limits or elastic pool limits. Articles, Hyperscale is only on single database at this point, right? So just be aware of kind of the limits, and the starting point for any investigation on single DB starts with sys.dm DB resource stats. One thing to note is that is different on Hyperscale is average data IO percent. And that in DMDB resource stats is only for the local RBPX IO. It doesn't cover, there's no governance today on remote IO to the page server. So that can be a little different than other tiers, and be aware of that. The other thing is service objective, aka the number of cores on compute, affects the RBPX size because RBPX or the resilient buffer, the non-covering cache on compute is 3 times the size of memory for that tier, and it indirectly affects IO as well. Right. The other thing is IO accounting. RBPX IO is exposed in DMVs. So you have kind of a DB ID 0 and file ID 0 in virtual file stats that actually has the IO done by the local RBPX cache on compute. One thing to note is all that IO is 8 KB. So there aren't even, there aren't larger than 8 KB. Whereas in traditional SQL Server, if you're doing a large read ahead, you can go up to 4 MB in chunks or multiples of 8 KB. All the IO is 8 KB, so the number of IOPS on RBPX could be more than if you were doing a read ahead. Note that there will be some governance, or there can be some governance even on the local SSD. Sys.dm IO virtual file stats does expose something called the IO stall queued read or write milliseconds, which is effectively the effect of governance. The other aspect is remote reads are an important part of diagnostic, in particular if IO is a bottleneck. So you have page server reads now, which indicate the read from compute to the page server, which are exposed as a column in most of the DMVs that track reads. So for example, exec requests, query stats, procedure stats, all have page server reads in those DMVs. Page server reads are also added to the execution plans, which we'll see in a second. One difference here that you'll note is effectively we need to protect in this distributed system. We need to protect replicas and page servers from falling behind because application of log is asynchronous, and so there can be cases where a page server replica is behind in applying the log, right? And we don't want to get to a point where it's so behind that it affects, for example, a failover, where on a failover it has to apply all this log and catch up before recovery can complete. So we have this log generation rate throttling. So primary log generation is throttled if it's greater than 100 Mbps. That's just at the primary. But the log throttling service, there's a concept of log throttling service, which also throttles log generation rate of the primary if these page servers or replicas are behind. If the slowest component is less than 1 gig behind, then no throttling is applied at all. If it exceeds that 1 gig limit, then the primary could be throttled. And the log generation rate of the primary can be reduced by 10 to 50%. So what is kind of the weights that you see on compute? You see a couple weights on compute. You see log rate governor weight. You see wait for RBIO storage. These stage, there are wait RBIO set of waits, and effectively they just show effectively what component is throttling the log generation rate on primary. So in this case it's page server, in this case it's replica, in this case it's destaging to log to xstore, right? Then from a waits and queues mechanism, otherwise other SQL Server waits are still used. Um, whether the page IO latch or write logs. And here's additional information in the Hyperscale performance diagnostics. Let's look at some of the supportability diagnostics, diagnostic information with Hyperscale. One of the first things to notice is this DMDB user resource governance. It's not different from any SQL DB, but helps you kind of know your limits. So, for example, we have ATV core, we have the primary log generation rate, you have the IOPS limit for the primary group, which is 204,000 for ATV core, and that is for RBPX only. How many page servers do we have to map this out to kind of architecture? I'm looking at sys.database files. Today, at least, it's a 1:1 mapping between file and page server. So as you can see, I have a ton of page servers, each of them 128 gig in size, and they're filled up pretty much. So I have 68 of those currently. The last ones are not yet full, but the allocated or max size is 128 gigs. Right. So the other thing is performance troubleshooting from an I/O perspective, because remote I/O is more expensive. All the hyperscale waits and I/O columns in existing DMBs. So some of those in DMOS wait stats have to do with the log throttling, and those are RBIO waits. As you can see, so I don't have a demo currently because of time on throttling, but depending on what is throttling log generation rate, you'll see that corresponding weight. Similarly, in each of the DMVs, you're going to have some column which has page server reads, whether it's total page server reads or in query store or some other column in procedure stats. So you can chart out, for example, from query store which are the ones that have the most of page server reads, right? So this is at the query level. Similarly, at the procedure level, there are counters for total page server reads. As you can see here, total page server reads, this CDB read medium is probably one of the highest, followed by the update, heavy procedure. One thing that the page query store does not have in the weights aspect is query store stores a category of weights, and so there is no granular hyperscale category, and so some of these weights get clubbed under the other bucket, if you will. Similarly, from query store perspective, you can get the average page server IO, and those are ones that are not being cached on compute, either because it's the first execution, if it's one execution, because things are cached in RBPX only after the second access once in buffer pool. Odd things like these update stats queries. You see the statman queries, update stats queries, so it was a scan, so it's not cached, in which case it can be kind of ignored. And then lastly, at the plan level, you see that the plan to in IO numbers has the page server stuff. So you have, for example, actual page server reader heads, which is pretty high, indicating that all this data is not coming from buffer pool or RBPX. If it was, then you would see the actual reader heads, there's actual reader heads be high, right? So you would see this number, but this would be close to zero if it was pulled from RBPX or buffer pool. Right. Similarly, if you look at a different plan, the same plan with data in buffer pool, the same I/O numbers would look kind of different. So you would see the logical reads, but you would not see kind of the page server reads. Actual page server reader heads or actual page server reads are 0. So those numbers are there in these DMVs as well. Last but not least, let's talk briefly about migration. Um, so migration, there's no database native restore. So if you're migrating from on-prem, this is a size of data movement, and movement is either with DMS or with any logical data movement tools such as BCP bulk copy, Azure Data Factory, Spark, or the Smart bulk copy sample. So in logical data movement aspect, of course, your data loading practices still stand. Bulk load into heaps for larger table, create index later, or if using cluster column store, use large batch sizes. Transactional or snapshot application also can be a tool to move data if you have primary keys and such. So you can use concurrent snapshot in this case, and it requires primary key on source tables. Migration from other SQL database tiers is just a change in service objective. Migration is done online, so your source is still online. But it's recommended to do this during a low write activity period because there is catch up. The way we do this is we actually spawn an instance in the backend with files on blob and log the log or transactions that are being applied to your current tier are then applied, and once they're caught up, then the cutover happens. The downtime is in the few minutes, it's less than 5 minutes. But if you have a higher write activity, then it'll take longer because it's not only seeding, it's also catching up, and the files are not necessarily on SSD. The log file is not on SSD at the point of catch up. Um, Currently, you cannot migrate to a prior service tier. We're working on something to enable that. You can restore to a point of time before migration if it is within the retention period. And then there is a source database size consideration. If your database file size on the existing tier is already greater than 128 gig, you land on something called 1 terabyte page servers. When we GA'd the service, we started with 1 terabyte page servers. These can sometimes not be performant if you have applications doing a ton of writes and small writes, because as you know, the files backing the page servers are on blob storage, Azure Blob Storage, and Azure Blob Storage does have a per blob limit. So the larger the blob, the possibility of hitting those throttling limits are higher. If a 1 terabyte page server causes perf degradation, one thing you can consider is creating a new hyperscale database and loading data into it. As I said, many workloads are not hit, but there are few that actually are impacted with this. Last but not the least, we have roadmap. We currently have TDE, BYOK, or bring your own key, or customer managed keys in public preview. We have database copy, which was lacking from a feature parity perspective in public preview. When it comes to database copy, there are two types of copies. There's the in-region copy. Those are a fast copy because they are copied from the snapshot. Then there is the cross-region copy, which is a size of data copy because snapshots cannot span storage accounts or regions today within Azure. There is reserved instance pricing, which is coming pretty soon, and we are working on bringing geo-replication to preview pretty soon as well. Last but not the least, there is continual ongoing performance and scalability improvements in the service, which enables us to improve the service continually from a perf perspective. Call to actions is, if you've not tried Hyperscale, try Hyperscale a try. Would love to hear feedback. Here are some relevant links. You can always reach out on email, and happy to answer any questions. Thank you for your time today. I hope you enjoyed the session.